All right. Well, thanks very much. Yeah, thanks very much for the invitation to speak here in this virtual format. Everyone can hear this? Sound is fine?
Yep.
Sounds great. Okay. Well, so yeah, it's a pleasure to be able to talk at CMU, where I know so many people and have had so many nice collaborations, interactions over the years. I want to talk about some work that I've been doing with a group of people listed on this slide here over the past roughly 6 years or so at this point. This began sort of around 2015 in some work that Ashton Anderson, Sendhil Mullainathan, and I were doing sort of at the interface of computing and behavioral economics. And I'll start with that work actually to sort of suggest where some of this came from. But we had found in some of the work we were thinking about as we were looking at human behavior, just the sort of rich ways in which, chess was showing up as a model system for many of the things that we want to do. And so as we thought about other domains, that were sort of, less of a kind of game nature, and more of even in the context of high stakes human decisions, we found we were often coming back to chess just as a nice self-contained environment where we could talk about human performance, algorithmic performance, the differences between them, the notion of error and mistakes, and all of this really played out quite naturally. And I think over time, what it sort of occurred to us was that it was proving useful for us as a model system for reasons a bit different potentially than the reasons why it's been such an effective model system for AI over the past 50 years. And that's we're now in a phase, where chess algorithms, of course, have really conclusively surpassed human abilities. And there's something interesting about studying creative pursuits in which that process has happened, right? An area which, in which algorithms are dominating so completely, and in particular, an area where that's happened despite a huge amount of investment of human effort, right? So if our goal is to think about areas where this has happened, I think it's particularly interesting, to think about that not in areas, which humans sort of don't pay much attention to, like adding long lists of numbers, but rather things that have these desiderata at the bottom, right? That it's really an area where, high levels of human achievement inspire a feeling of mastery, people train through their whole lives. Similarly, over, even like a century or two of time scale, there's an enormous amount of scholarship built up. And yet, despite all of this, it's an area that, if the goal is to, succeed at the objective algorithm, humans have nothing to offer at this point, right? And so it was interesting to us that chess has these properties, right? That if the goal is to win chess games, then algorithms have conclusively passed humans, despite the amount of human effort that's gone into this. And in that sense, it also proved interesting that, in a world where we often find people, writing for the public and speculating about, what will post-human mathematics look like, what will post-human, prose writing look like, what will post-human art look like, and all of that, tends toward the extremely speculative, that there are domains where you can ask that question very concretely, and chess is certainly a key example of that. So that was, I think, sort of the outer framing for why we were particularly interested in this. It's, of course, interesting to talk about, I was sort of happy to have the opportunity to talk about this at Carnegie Mellon, because obviously if you were to think about sort of a single institution where, chess as played by computers or played on computers is embedded in the history, it would certainly be CMU. And I think what's interesting, obviously, is that through most of the history of computer chess, there's been, all through the 20th century, there was a look forward to a sort of moon landing like event that everyone had in mind, which was to surpass the abilities of the best human beings in the game. And so what's interesting is how over the past 20 years, that goal is now in the past. The field has achieved that goal, and as a result, we can now actually do this new activity, right? This activity of looking at what does post-human chess look like, right? And as I'll talk about, and this is in fact part of the point of the talk, there's no sense in which humans have lost interest in chess, online chess, and again, thanks to pioneering work like Danny's with the Internet Chess Club, online chess is, as popular as ever and more so. Professional chess is very active. You still have people, as strong as any through human history. So human interest in chess hasn't gone away. We are in sort of a post-human era when it comes to winning chess games, right? That humans really don't have much to add there. And so there's sort of three questions that I wanted to ask, motivated by that. One is, can we use the power of chess algorithms to now turn this around and analyze human behavior, right? So take chess algorithms, not think about the goal of winning chess games, but rather the goal of analyzing what humans are doing when they play chess. Second, if we can do some characterization of human ability, human error, can we actually design algorithms whose goal is not to win games, but to match human moves at different skill levels as closely as possible? And finally, I think there's sort of an interesting opportunity here, again, to sort of move things from the realm of speculation to the realm of the concrete. How does the ecosystem of professional chess, for example, look different now than it did 50 years ago, for example, now that you have chess engines? And again, there has been a lot of informal writing about this topic, and there's actually a chance to look at some data and talk about what's actually changed. Okay, so with that in mind, let me plunge into the beginning of the story here. First, just to establish the extent to which algorithms have now exceeded human beings, a brief history. The first time a computer actually beat a human grandmaster under standard tournament conditions was 1988. Roughly 10 years passed, and then in the scene depicted in the upper right here, Deep Blue famously defeated Garry Kasparov, the world champion at the time, in a 6-game match. After that, there was much less public focus on human versus machine as the machines began to get better and better. By 5 years later, Deep Blue, of course, ran on an IBM SP2. It was an incredibly powerful piece of hardware. By 5 years later, desktop computers could hold world champions to a draw. By 2 or 3 years after that, the best humans in the world couldn't really compete against desktop computers. And so the last time you actually saw a human being beat a desktop computer program playing chess under standard conditions was 2005. By 2 years after that, computers could offer, the best players in the world, things that strong humans offer to weak humans, namely like pawn odds, knight odds, I'll give up a pawn, I'll give up a knight, things like this. After that, obviously, humans basically stopped playing algorithms in public, except in sort of extremely specialized places. You can also look at this in terms of chess ratings, and because we'll be using chess ratings as a kind of one-dimensional scale for thinking about this as I talk, it's useful to kind of just have some rough numbers in mind. I should also say this talk is not going to involve us going through elaborate chess analyses or analyses of chess positions, so it's enough, for purposes of the talk, just to think about chess as a two-player game. I'll show a few chess positions, but we're not going to really get much into them. But one piece of orientation that's useful to have is the ELO system designed to rate chess players. And it's actually an interesting fact in itself and the subject of its own body of research, why it is that a one-dimensional measure should be such a good predictor of the outcome when two people play each other in chess, right? It didn't have to be this way. It could have been that chess skill was highly multidimensional, and there was not a single number that was really very good at telling you what someone's skill was. But that didn't turn out to be the case. This one-dimensional number has been surprisingly effective in practice. And so, you should think about these numbers just in practice as saying that, amateur chess players tend to range roughly kind of 1,000 to 2,000, 1,000 to 1,800. Someone who's 1,800 rated is quite strong for someone who plays chess as a hobby, although, not in any sense extremely good at chess. People who really, devote huge amounts of time to chess and become extremely good get up to 2,200, 2,300. And then at some point, if you're actually one of the top players in the world, your rating gets above that. And, the best human players are at 2,800.
Can I ask a quick question?
Sure, please.
I've forgotten what the statistic is, but there's a definition for ELO. I think
so if
maybe 100. Go ahead. Yeah.
Yeah. So you're saying a 400-point difference means basically a kind of 90 and 95% chance that the better player is going to win. Yeah, so it's basically every 100 points, it's about a 3/4 mark. And then if you exponentiate that, you're going to get, so you should think of it as a sort of, when there's a 400-point difference, the outcome is almost determined. Obviously upsets happen, but you're sort of in the 95% range right. And actually, chess is therefore interesting in sort of how many different 400-point jumps there are, right? So there's interesting empirical research on the different gradations by skill, and chess has many levels of skill, right? So in which I have sort of tranches in which, at one level you can almost conclusively beat the previous level. And so the point here is that it's sort of hard to rate chess engines on the same ELO scale as humans, just because you sort of need actual competition to actually set the ELOs for the reason that Danny mentioned. You actually need to see the win-loss outcomes. But to the extent that people do at current chess engines, they're clearly above 3,300. So they're as far above the best players in the world as the best players in the world are above, strong amateur players, and more so. And there are even interesting questions about, at some point you have to ask, like, at what point do we start bumping into the game tree of chess, right? If the game tree of chess, because in the end chess is a two-player perfect information game, with perfect play, that may have some rating which would not be infinite, and it's not clear where that is. But there's an interesting debate as to how close chess engines are toward that in terms of rating. Obviously, they're not playing chess perfectly. Okay, so our goal here is to look at human behavior as a starting point. And so, the reason why Herb Simon called chess the Drosophila of psychology and John McCarthy called it the Drosophila of AI is because it presents you with this very well-defined closed world sequence of tasks. Every single chess position is a new problem that has to be solved. And when the player chooses a move, we can, we have the task instance, that's the position. We have the skill of the decision maker, the ELO rating, and we have often the time they had available and other things. So let's start just by saying, given a position, can we tell if someone's going to make a mistake, right? So the whole problem is like shown in this photo, which is a screenshot from a video of a blitz game played between the player on the right, Magnus Carlsen, believed by many to be the greatest chess player of all time and the current world champion, and Peter Fiddler on the left, ranked roughly 10th in the world. And someone's hand is hovering over the board, they're about to make a move. You can say, given the position, given the rating of the player, are they going to make a good move? Now the question is, how do we talk about what's a good move? It'd be tempting to use chess engines to evaluate moves. After all, we have just spent a few slides saying that chess engines are extremely powerful. Why not use them to decide if this is going to be the best move, right? So we could take, this position on the chessboard, we could find the corresponding game on the internet, take the moves, plug it into Stockfish, which is sort of the canonical open source, super powerful chess engine that anyone can download onto their phone or PC. And we could run this position through it, and it tells us that it thinks that what Peter's Fiddler should do right now is move the rook forward 2 squares, rook to c4. And that would give us some, so we could ask, so does he actually do that? Now, the issue here and the challenge with doing this to evaluate errors is that sometimes a player makes a move and it's just clearly a mistake because they've changed the value of the game by a huge amount, this heuristic evaluation. But the problem is that the numbers that chess engines are using, chess engines don't have access to the game tree of chess. So they can't actually tell you if you've changed the win-loss outcome. They can just tell you that under their heuristic function, you've changed the heuristic function by quite a bit. And of course, that enables them to play chess well. But sometimes these are questions of taste, right? If a player makes the second best move according to the engine, then the engine believes they've made their life more difficult, but the engine doesn't know if they've actually changed the outcome of the game, right? So this is sort of the gray area that makes it hard to use engines for this purpose. Here's something else you can do, and this is actually what we did when we began looking at this. We can focus on a subset of the game when there are very few pieces on the board, right? So if I play this YouTube video forward a bit, 3 more minutes, it is blitz chess after all, we get to a situation where there are now only 5 pieces left on the board. And now we're in an interesting situation, because if we want to evaluate people's mistakes in this very sparse regime, we can use the fact that chess has in fact been solved for positions with at most 7 pieces on the board, right? This is no longer the realm of chess engines. This is the realm of table lookup, right? And all of us in computer science know the power of table lookup. If you get to a point where you have a finite constant size problem, you can just write down every possible instance and just write down the answer. And you can do this for relatively large constants. And so what so-called table bases have done is simply recorded, and these are multi-terabyte size databases, every single way of placing up to 7 pieces on a chessboard. And then by dynamic programming, they just work, they started all the positions which are checkmate or stalemate or a draw. And they just start moving, 1 step away, 2 step away, and so forth. And so, once we're a few minutes further into this video and we get to this position, we can take this position and just plug it into a table base. We get some output like on the right. This no longer looks like Stockfish, which is giving us a kind of heuristic guess at the best move, a very good guess. Rather, this is something which is simply telling us that if you were to take this rook, which is on g3, and you were to move it to the left to b3, then you'd be on the path toward a forced win in 15 moves. If you moved it to g7, then you would be on the path to a win in 17 moves. But you could do other things. If you were to move it, in some other direction, like you pull it all the way back here to g1, you've actually thrown away the win. You've changed the minimax value of this two-player game from a win to a draw. Okay, and so when table bases first began to appear in the early 1990s, a lot of sort of eloquent writing was said about them, as in this quote at the bottom, that people were sort of amazed that this is literally optimal play and something that we never thought we would see optimal play, right? That this feels like the truth, and it's often sort of incomprehensible to humans. But to a table base, all positions are equally easy or difficult. It just looks things up. Okay. So that's the, and actually, if you play this video forward a few more seconds, you'll discover that Magnus Carlsen, the best player in the world, reaches out, grabs the rook, pulls it back one square to g2. And we look up rook g3 to g2, and we discover that Magnus has just thrown away this win, right? He had a forced win, and he put the rook on the wrong square. Okay, so we'd like to do this not with frames from YouTube videos, but rather with huge amounts of data from people playing. And so if we want to look for what are the features that are predictive of errors? Like, was this a particularly hard position? How is it the best player in the world with 5 pieces on the board, made the wrong move, threw away the win?
I have a question. Right? Did Magnus win the game or not?
He did win the game because there were several more table-based errors after that. And that's another important point, is that in the end, we're taking individual instances. But of course, a game is a kind of Brownian motion over these instances that leads eventually. And one argument I'll come back to, actually, which is crucial, and we'll see this in some of the data, that the best players in the world, it may not be that they're perfect on every move, but that there's a positive drift toward a win. So certainly a big piece of what's going on. Yeah, good question. So our 3 data sources, the first is about 1 million games played by the strongest players in the world, so we can look at this. Second is several orders of magnitude more, several online chess servers, where there are roughly 1 billion games being played by strong amateurs, all of which, is available as data. And so we just have a huge amount of data for looking at these things. And we can just take all instances with about 6 pieces and ask, did this change the minimax value? Okay. So from here, we actually now have so much data. Let's just jump to some plots, right? So the empirical blunder rate is simply, in these positions where we know the minimax value of the game, how often did that value change? And so I'm going to show some plots where on the x-axis we have some variable of interest, like say the rating of the player. And the y-axis we have the fraction of all times that they change the minimax value for the worse. Obviously, you can't change the minimax value for the better. Here's sort of a first thing you'd want to see, like, do better players make fewer blunders? And the answer is yes. So and all of these plots are going to be quite smooth because we have just so much data. So this is on the free internet chess server. And, you see that in these endgames, a player rated 1,000 changes the minimax value about 10% of the time, player rated 2,000 about 5%. And of course, the best players in the world significantly less, from 2% to 2,300 down to about 1% to 2,700. And again, for calibration, there are about 50 players above 2,700 in the world, right? So these are the best 50 players in the world. Okay, how should we decide let's have some simple stratification of the difficulty of the instances. And my plan here is to start with some very simple measures and then talk about something infinitely more complicated where we actually sort of essentially throw industrial strength machine learning at this question. But let's start with things that we can interpret as, as human beings looking at this. Arguably the simplest measure of the difficulty of an instance is what we could call the blunder potential, which is, again, you have some moves at your disposal. Some preserve the minimax value, some change the minimax value. So you could say the blunder potential is the probability of blundering, changing the minimax value, if you choose a move uniformly at random. Right? And so, for example, in our running example here with 5 pieces from this Magnus Carlsen game, there were 18 legal moves, and 9 of them changed the minimax value, so the probability of blundering at random is 0.5. It's interesting that this heat map shows that actually your probability of blundering in practice is actually just going up monotonically in the blunder rate, in the blunder potential. This is a little surprising, actually, because if you think about, what we know about hard computational problems, the hardest problems are generally not the ones that have a unique solution. And even just intuitively in chess, you would expect if there's a unique solution, maybe it's going to be obvious to you. That appears not to be the case in aggregate. Obviously, there are certainly situations like that, but in aggregate, blunder rate goes up with blunder potential. Okay, so we have a few things, right? So we have the skill of the player, we have the time remaining, we have the blunder potential, but I want to talk about sort of two in particular, and that is the skill of the player and the blunder potential of the position, right? This kind of skill versus difficulty plane, if you will, because this is a very interesting construct, right? This is basically saying, and this doesn't just apply to chess, this applies to any situation when you see a human being doing something. Their performance is dependent on two things: how good they are and how hard the instance is. This applies to driving, for example. Would you rather be a good driver on dangerous roads or a bad driver on safe roads? Is something about the skill versus the difficulty. And the point is, in many domains, this is very hard to get your hands on with any significant amount of data. But in this chess domain, we can really get at skill versus difficulty. Okay, and so that's the question that I'd like to ask next. So you've seen these plots before. This is simply skill versus blunder potential. So let's now stratify this by the blunder potential of the position. So what I'll show next is some plots that look like this one, except that instead of just one curve, I'm going to have a different curve for each discretized version of the blunder potential. So in other words, there'll be one for blunder potential 0.1, 0.2, 0.3, and just going up. So intuitively,
I have one question, John.
Yeah,
can I ask a question? Yeah, somehow, isn't it just an indication that your definition of blunder potential is not really reflecting difficulty? Because what really reflects difficulty is how often the players make a mistake, and not your definition of blunder potential.
Agreed. Yeah, no, I don't think blunder. In the end, empirical blunder rate is the interesting thing. But here's the interesting surprise, which is how much blunder potential as a feature is sort of controls things relative to player skill, right? So these are all the different blunder potentials. And the point here is that these lines essentially are non-crossing, right? So a player rated 1800 will almost always beat a player rated 1200. And yet they're more likely to blunder in a position of blunder potential 0.8 than a 1200 rated player is in a position of blunder potential 0.7. And a player 1800 is more likely to blunder in 0.7 than at 0.6, and so forth. And this, even if we go over to the best players in the world, a blunder potential of 0.8 is really quite difficult, right? Someone rated 2700, one of the best 50 players in the world, more likely to blunder in a position of blunder potential of 0.8 than someone rated 1200 is in a position of blunder potential of 0.2, right? So the difficulty actually, the empirical blunder rate goes up very sharply in this quantity, which was a surprise to us, right? That the measures of the difficulty of the position are much more significant. But again, I agree that this is only scratching the surface of difficulty. We want to get further into this. Now we have enough data here that there's no reason to actually, and this sort of is one step toward your question, Shai, there's no reason to group things by blunder potential. What we should really do is actually group things just by position, right? We have enough data that we should actually just fix the exact position, because in our data, there are many, many positions that have shown up at least 1,000 times verbatim, right? These are sparse positions in the end game. And so, over 1 billion games, you're going to see the same position over and over. And so for this exact position, I could say, let F sub P of R be the blunder rate of players of rating R in position P, okay? Right, and so this now lets me control for everything, and I'm only looking at the rating. Now, it would be natural, to assume there's a certain monotonicity condition, right? We saw in aggregates that all these curves go down, right? Everything goes down because as you get higher rated, the blunder rate goes down. And so we could call position P skill monotone if F sub P of R is decreasing in the rating R. And obviously a natural conjecture is that every position is skill monotone. But this turns out not to be the case, actually. There's actually a relatively wide variation in these things, right? So many of them just go down. Most of them do. But you can find unusual positions where it actually goes up. where higher rated players consistently make blunders at higher rates than lower rated players. And these appear to be, I'll start showing a couple chess positions in a second, just so we can get some sense of this. The question is why? And I'll say actually what's interesting is that these exhibit things like reflective symmetry. So these ones where the curves go up, which I'll call skill-anomalous, have, if a particular position is skill-anomalous, the left-right reflection is, as is the black-white reflection. Yeah, Nihar, question.
Could there be confounding factors like just having a bad day? That is, a certain position is bad, and so a player with good ratings might end up there only if they're having a bad day, and then it'll reflect in a higher blender as well because they're having a bad day.
It's a good question. I'll show you the positions. Some of these positions have only king and pawn versus king, so they're extremely basic positions. Yes, so we've discussed this with a few chess grandmasters actually, and part of it is getting over the with chess grandmasters. First, you have to convince them that anyone could ever blunder in king and pawn versus king endgames because they find this hard to imagine. But it appears to be things where there's a certain rule that you're supposed to obey, and you sort of visually seem to be violating in these positions, and that seems to greatly affect things. But yeah, let me sort of show a couple chess positions. And again, keeping with my promise, I'm not going to delve into much chess analysis here, but just to share a few things. So, I mean, first, just the range of different per position empirical blunder rates are enormous, right? So this is a scatter plot of frequency of positions cut off at 100. So we're only taking things that occurred at least 100 times. And then on the y-axis, the empirical blunder rate, and this is a scatter plot. And these are just from the Pareto frontier here on the right, are just a few examples of positions. And these are almost sort of like, organic frozen instances from nature of sort of chess puzzles that have emerged on their own, right? So this one in the upper left is actually emerges as a Q chess problem. It's appeared 140 times in the free internet chess server in the course of games. One time somebody found the right move out of 140 occurrences. Others of these also, just moves that are very, very hard to find. This is the one that's actually, among all ones with three pieces, with king and pawn versus king, this is the one with the highest empirical blunder rate. Let's pick this one out, actually. Like, why does this have such a high empirical blunder rate? Of course, we can't know, but in the work with Sendhil on this, it became interesting to think about some of the behavioral questions here. And certainly one possibility that seems intriguing is that in this position, which has a blunder rate of 3/4, right? 3/4 of the time people make the wrong move here. You're supposed to drop the king straight back and not go this way. Even though if I translate this position anywhere else on the board, you're supposed to go back diagonally and not drop straight back, right? So it appears that there's a kind of failure of analogy here where what you're supposed to do everywhere else on the board is not what you're supposed to do in the corner. And in fact, it's not just that you have freedom here, it's that it actually reverses. Maybe something similar is going on with these skill-anomalous positions, right? And again, I'm not going to get into much of the chess detail here just to have the talk be self-contained, but effectively, the sort of most frequent skill-anomalous position is one where you come to a moment when you're supposed to push the king forward. But apparently stronger players more typically push the king behind the pawn to kind of mark time, sort of somehow they're concerned that this is the wrong moment to push the king forward when in fact it is. So it's interesting to think about sort of the questions here. And again, a lot of this is more surfacing open questions and hypotheses than actually providing insights about mechanisms. I mean, of course, there's sort of interesting just to think about many of the sort of implications of this. One is simply, looking at an array like this sort of reminds us how much this is missing when you teach skills like chess or like other things, right? If I think about the sort of typical way I would organize a chess book about endgames, it'd be sort of taxonomical. It would say, these are the things you need to know. This is the kind of overall structure. And it would sort of give roughly equal coverage to all of these things. But of course, the empirical data says there are many things, this position down here in the lower right, people blunder 1 out of every 200 times. So this position, you could effectively tell most players, don't worry about this position. You'll do the right thing when you get to it. right? And so it's sort of telling you that in terms of time allocation, there's some things that are extremely difficult yet frequent, and some things that are extremely easy and also frequent. And so I think it's sort of interesting to imagine this as just an extra dimension that's often invisible when we organize content for things like pedagogy. Okay, good. So this has all been about very sparse endgames, exact min and max values, interpretable features that we can talk about and we can make hypotheses about. I want to, and I realize we have limited time here, I want to talk about some things that we've been doing recently. And in this, Ashton and I've been joined by Ashton's student, Reid McIlroy-Young, Russell Wang, an undergrad at University of Toronto, and Siddhartha Sen at Microsoft Research. You know, to come back to this question of, can we analyze, you know, human decisions in unrestricted chess games? And I want to move from sort of, you know, recognition to generation in a sense, to say, you know, given a position P encountered by a human player of ELO rating X, can we predict the move that the player will make? Okay, and so, again, as a sort of continuation of this analysis of human behavior, and also, you know, the question of, if we had a system whose goal was not to win chess games, but to mimic human play, how well could we do? Now, and I'm going to sort of imagine this is sort of parameterized by these two parameters, but sort of in a cascaded way. I'm going to imagine building an algorithm that has, you know, that's parameterized by this rating X. So there might be a different one for each rating X, and then it will take positions P and make predictions about them. Okay. Now, it's sort of difficult to adapt chess engines like Stockfish for doing this, but while we were in the middle of this research, a very promising opportunity came along with the development of AlphaZero by DeepMind and the sort of rapid creation of open source versions by the chess programming community through things like Leela, right? So these work through deep reinforcement learning, right? They have no human built-in knowledge, and they basically train themselves through self-play. But they give us an architecture that we can try adapting for this human prediction problem, and that's what we did. So we start with Leela as a network architecture, and we say, okay, in Leela, which is basically designed to look like AlphaZero, you know, there are basically two main heads on the neural nets. There's a policy head that's outputting a move, and that's optimized for you know, making moves that win, and there's a value head, which is trying to estimate the win probability. Okay, and then it trains itself through self-play. It just generates as many games as it wants by just rapidly engaging in self-play. So in Maia, we're going to shift that. We're going to say the policy head again specifies a move, but now it's being optimized for matching with humans of the given rating, right? So this is Maia sub X, Maia parameterized by X, the rating, and it's trying to match the human moves. And it's being trained now not through self-play, but with the billion human games that we find on Chess. Okay. And again, an interesting feature is that the value head is still actually estimating a human win probability. But again, the loss function is about matching with people. Okay. So what would it mean to succeed at matching moves, right? So we'd like to create an algorithm parameterized by X that takes a position P and predicts the move made by a human of rating X. And it sort of felt like, you know, we sort of drew these cartoon pictures at the beginning, like you would expect that, you know, so we'll have one that's rated, you know, 1100, 1200, 1300, and so forth. And you would expect that the performance should peak at the rating that's built into the engine, right? So if I optimize for, you know, 1600, then, you know, this curve should peak at 1600. If you have the best performance there, it should fall off in both directions. And obviously, you know, before we do any of this, we should ask, maybe standard chess engines already solve this problem. Maybe they already are good at predicting human moves. We, of course, suspect they aren't. Anyone who's played a chess engine, you know, at a very low level suspects they aren't. What you tend to do with chess engines is you dial them down to this very, very limited search depth, or this very, very limited level of computation. And you therefore make them easier. And so it's sort of competitive with you. But people always have the feeling that when they play engines, they've been attenuated to make it a sort of fair match, but they don't look like humans. Their moves don't look like humans. They look like a mix of sort of inexplicably good moves and extremely bad moves that somehow balance out to this outcome. But now we can actually run the empirical question. What does it look like as we limit the depth of Stockfish and try to match human moves? And so this curve was already interesting to us because it says something about how much Stockfish resembles or doesn't resemble humans that we really hadn't known prior to at least running this test. And so, first of all, these curves all go up, right? So it says, if I would like to, each of these things gets better as the human gets better. And there's a different curve for each Stockfish depth. And actually, there's something weird that we don't fully understand, the non-monotone, which I won't delve into for this talk, but sort of thought-provoking, that Stockfish depth 1 is one of the best depths for matching humans. It gets worse at depth 3, depth 5. 5 is the furthest from humans. And then it starts to rebound. It gets better at 7, better at 9, and then is best of all at extremely high depth. Okay, and so, right. And so that's basically saying the depth is not really so closely aligned with accuracy and move matching. Leela does a bit better than Stockfish. And so this is Leela at different ELA ratings. The better ones go a little bit up with it, skill. The worst ones go a little bit down with human skill, but actually it's remarkably flat with Leela. It's about equally good at matching humans, ranging from weak amateur to very strong amateur. Okay, so, but what about if we optimize on human moves? And so with Maia, we end up with two things. One is significantly better move matching. And secondly, these interlaced curves like we were sort of hoping to see.
I'm sorry,
Question.
I got confused with the those charts.
Yeah.
Could you go back to the one, just the one, no, not, well, whatever. I go back to the one with Leela.
Yeah, there's Leela.
Okay, so you're saying if you run it, this is a specific chess engine at 800. That's the lowest one. The
Lowest one here, yep.
And you're telling Leela something to make bad moves?
Yeah, so this is a heuristic built into Leela that basically limits the amount of search so that it does deliberately badly, as in it makes bad moves.
But
So it's being constrained.
How could it, like, some of these curves don't change at all as a function of rating. So they're saying they're predicting the human move.
Yeah.
It doesn't matter what the rating of the human is. They're predicting at the same accuracy. The 40% line, for example, it's up there.
Yeah, it's strange, right? It's incredibly flat. So, I mean, let's at least talk about what the experiment is. The experiment is I take 1 billion games and I stratify them by human rating. These are games played between humans. And I say, okay, here's a position. And I simply run the position through Leela, say rated 2700, this flat line of 0.4. It outputs a move. And I ask, how often does that match the move made, let's take 1700. Take all games played between 1700 players on Lee chess. How often does it match, does Leela, now Leela's not trying to match humans. Leela's just trying to make a move. But it's a well-defined question. How often is that move the same as the one that was played in the game? And the answer is 40% of the time. And what's weird about Leela is that number is 40% no matter, now I move over to a disjoint set of 10 million games played by 1800 players. And I ask, how often is the move played by Leela the same as the one played by the humans? It's again 40%. And I move over to 1900. How often? It's 40%.
Well, what is
I don't see any.
What is the rating of that version of Leela?
The flat one is that's the 2700 rated version.
So it's way better than all these players. So
way better than these people. Yeah, there's no question who would win, but we're asking how often it matches their move.
It's almost like the person just gets lucky and makes the right move, but quote unquote the right move. But the funny thing is the weak player makes the right move about as often as the strong player. They're both clueless. I guess.
With respect to Leela, correct, yeah.
Yeah, okay, sorry.
I mean, Leela, of course, is not the game tree of chess, so it too is doing it. But yeah, this is sort of just,
so
it drives
Does it mean that if I try to predict Leela's moves, I will be as successful as if I'm a weak player or if I'm a strong player?
So there's an endogeneity here, which is important, which is weak players don't end up in the same chess positions as strong players do. They end up in, right? So the extra bit of triangle inequality here is that if you're a strong player looking at games played by weak players, there's often just a sort of obvious capture you can make because somebody left a piece hanging, for example. And so there's a question about the inherent difficulty of actually making good moves in a game played by 1100 players versus 1900. And that also affects them. but yeah, so it seems to say that games played by weak players, there's a kind of arbitrage opportunity, or there's a no arbitrage notion here, which is that there's about the same level of sort of being able to cash in on good computer moves there that there is in games between strong moves.
But that's
both the endogeneity of the moves. And, yeah, sure.
Sorry, just a quick question. How are you limiting the strength of this engine?
So this is a heuristic built into Leela, which is, so Leela's built on Monte Carlo tree search, and basically there's a kind of tunable parameter there. So that's not us limiting us. That's just taking different builds of Leela, basically. Yeah.
I see. Understood.
I have a question too. If there's not a confound, whether it's the beginning of the game, the middle of the game, or the end of the game?
Yeah, absolutely confound. Yeah. So these results are roughly the same. So we tend to cut the opening out. So we try to get 10 moves in, because obviously a lot of even weak players play the opening through memorization, and so they're often indistinguishable from very strong players until they get out of their opening repertoire. So we so you see a lot of artifacts in the first 10 moves of the game, and so we basically cut the first 10 moves off when we look at it. Similarly, you tend to get similar results whether or not you get into the late end game. Although, as you've seen, even in the late end game, you see high rates of blundering and high rates of disagreement with optimal play. So the results aren't that strongly affected by. So in the paper, there are some plots showing the move matching as a function of how far into the game you are, and you see a lot of weirdness in the very beginning, but after that, it smooths out.
Okay, thanks.
Yeah. So this summary just shows how there are a lot of just counterintuitive features of what it means for computers to both be good at chess, and for humans to be good at chess, and for humans and computers to play nothing like each other. Right? It's sort of, one really has to internalize just sort of some of the counterintuitive things of that. But the point is, all of these are chess engines trying to win chess games, right? In contrast, this is, right, whereas Maia is actually trying to solve the prediction problem. And so, you could look at this, so again, this is sort of now parameterized by each possible rating. And so the performance of each of these, there is a kind of string art aspect to this, that each of these peaks at the rating that it's trained on and falls off. It's again, sort of a striking fact about the one-dimensionality of the rating system, and it's how reasonable an approximation it is, that you actually get this, that there is such a thing as 1400 rated chess, or there is such a thing as 1500 rated chess, at least to some extent, in that these curves are unimodal. And so this is all of them put together just to see absolute comparisons. Stockfish, Leela, which is a little better, and then Maia. And so there's sort of two ways of looking at this gain, right? The gains are, on the one hand, non-trivial, right? We're getting sort of 5 to 10% improvement over engines. On the other hand, we're only getting that much, right? This is an algorithm that's focused using the entire architecture of Leela, trained on 1 billion human games to try predicting human moves as well as possible. And it's not, getting dramatically better than Leela, which is trying to win chess games. On the other hand, it is getting non-trivially better. Okay, so that's the comparison. And what's interesting, of course, is that, yeah, please.
Yep, sorry. What is the limit of accuracy here? Like, there is some entropy in human moves that just theoretically limits the maximum accuracy that you can get on this problem. Do you know what that might be?
Yes. Right, so most of these are on, most of the game has many pieces on the board, and it's hard to, so we're actually beginning to do some tests on sort of reproducibility. As in, we've sort of been working through some IRB approval to now be able to run some human tests on trying to estimate something about exactly this question about the entropy in human moves. One hint certainly comes from endgames, where we see in these games that occurred verbatim, 100 times or a few hundred times, that that we have some notion of the distribution of moves which are made, and as we see from those plots, that's relatively high. Right, so there is some absolute limit, but it's hard to get a number here, just because obviously we're going to need some. We're not going to be able to do it from the data. We're going to need some model, because most of these positions occurred only once, and so there's not, unlike with the end games where we could actually start to get at that number. It's going to be hard here. But it's a very good question that we're going to try to get at through some human subjects work that we're doing over at the moment. Yeah, definitely. Yeah, very nice question. It's intriguing just to think about the way you can take a single position, of course, and look at Maia at different ratings. and watch how the predicted move changes, right? And just, again, I sort of trying to keep with my promise of not delving into too many chess positions here. You're not supposed to necessarily, get into the intricacies of this. Just to notice that, this is a game played by a player who was roughly 1300 rated. The move they made was b6, which was to push this pawn forward. Hint, this is actually really not a very good move. Stockfish, of course, can't even comprehend why they would do that. Stockfish wants to play pawn takes a6, which is the natural move to make in this position. And as you turn up the rating on Maia, right, so you run the 9 versions of Maia, the bottom 4 predict this move that really makes no sense if you're doing minimax research. It's just a bad move. But it somehow correctly predicts that humans are going to make it, and it stops predicting that at 1500, right? So you can sort of see the rating at which you predict people will stop making this mistake. Again, this is a single anecdote out of hundreds of millions of anecdotes, so it's, but just sort of to show the kind of information that you get out of an engine like this, right? That you can actually dial up the rating and sort of see how the move prediction changes. We released this onto Chess. It had been playing in stealth mode for quite a while. And then once we wrote the paper and had everything kind of set, this very nice implementation that Reid, Ashton, and Sid had built into the Chess API, it got turned loose and began to play with a lot of people, and the number of YouTube chess channels began to sort of play games against it, which got so at this point we have 3 of them. You're welcome to go try them. The 1100, the 1500, and the 1900. The 1100 one has played 300,000 games at this point, which makes it the 3rd most played player on Chess, and the 1500, 1900 have played each about 100,000 games. There's the 1100. There are various design choices if you want to create a bot that does this. The 1100, we made a slightly non-obvious choice, which was it always makes the highest probability move rather than sampling from the distribution of moves, right? So the output head gives you a probability distribution over moves. And one thing we are revisiting is the question of should it actually choose from the distribution? Because when it plays the argmax, it's better than 1100. Because if you were to think about an 1100 rated chess player and say each time they play the move that they would most often make, then they'd be better than 1100, because a lot of their lost rating points come from idiosyncratic mistakes that they rarely make. So there's even questions about sort of how do you actually, once you go into generation mode, how do you actually do this? But it's been interesting, just this sort of qualitative feedback from players, and we've gotten over the course of 500,000 games played on the site, a lot of user feedback, and definitely just a lot of people saying that this experience feels more human to them, that compared to playing bots, that the kinds of things it's doing feel much more human. And it's of course always nice to get approving tweets from Gary Kasparov as well. So okay, so I wanted to do one final thing. I realize I'm sort of way low on time here, but in 5 more minutes, here's a completely different question that I alluded to at the beginning, and what has been intriguing to us this entire time. And so we decided here too, there's data, and there's no reason not to actually use the data and see what we find. So in the sort of spirit of wrapping up, back to this notion that it's interesting to look at, sort of rich, creative human activities in a post-human world, right? And we can't do that for math, we can't do that for writing, we can't do that for art or music, because algorithms are not yet sort of really, sort of intruding on human territory there nearly as much as they are in chess. But chess is this very refined art form, where computers are just an enormous part of the landscape, right? And so if 2005 to 2007 was sort of the chess singularity, where chess, machines achieve chess superintelligence, can we see any of its effects on the ecosystem of professional chess, right? Anecdotally, we know that there's an enormous impact. I mean, not just anecdotally, but top chess players spend all their time training against chess engines. And the whole style of play feels like it has changed. And there's some folk wisdom about what the effect was, right? That top players can now come from any country, right? The idea that the world champion is Magnus Carlsen from Norway, a country with an extremely limited chess tradition, and that he could get this good at chess by playing chess, computer chess in his bedroom as a teenager, is sort of amazing, right? That in the 1970s and the 1980s, if you wanted to be, the best chess player in the world, you sort of essentially had to grow up in the Soviet Union, had to sort of, go to sort of the Central Chess Club in Moscow and be trained from a young age and work with the best people. Yeah, thanks, Danny. Right, when Magnus was on his computer in his bedroom, a lot of it was on ICC. A very nice point, right? And compared to the 1970s, and the whole mythos around Bobby Fischer was that it was almost inconceivable that a loner from Brooklyn, in the US, a country that never really took chess that seriously, could actually be competitive with these people who had an entire culture supporting them. But that was, a kind of once in a century aberration in a sense. Right now, it seems to happen much more frequently because any country you grow up in, you have this, as many sparring partners as you want, right? And there's similar things, right? Now that everyone's training with the same chess engines, there's a kind of monoculture that emerged, right? They feel like there's sort of a homogenization of style. And so, there's been a lot written about this. This quote from the New Yorker nicely sums up all three of these cliches in sort of an incredibly compact way, right? So Kasparov saying that, everyone now looks through the computer lens, and certainly before the age of online play, it would be nearly impossible for someone from Norway to rise to #1 by the age of 19. Okay, but in the end, all these things are empirical, like these are all empirical conjectures, right? Like either all of this did happen or it didn't. And so obviously everything here is documented well enough that we should be able to ask the question. And the answer, and again, I'll show some data that's more in the spirit of posing questions than explaining anything. The answer is a bit surprising. So I'm going to show you, let's start with country. I'm going to show you the x-axis is year. Year is going to go forward. And the y-axis is going to be the geographic entropy of the country that the top 300 players come from. Okay, so top 300 players define some distribution over all the countries of the world that has some, distance from uniformity. Let's see what that distance is. Okay, so up is going to be more entropy, right? People can come from any country. And sure enough, there is a gigantic jump, huge jump. Unfortunately, that jump happens in the year 1992. Right, when not much was, when chess programs were not really a big feature of the landscape. 1992 did correspond to an enormously significant event in chess history. It was the end of the Soviet Union, right? The end of the world's largest state sponsor of chess had suddenly come to an end, releasing tons of people whose previous nationality was Soviet Union into the world, who were now playing for all sorts of different countries. What was happening in 2007? Almost nothing. Right? The geographic entropy did not change almost at all. It's not clear to us what this means, but it certainly means that at least some of the folk wisdom about people who come from any country is not as obvious as it seems. This is not to dispute that it's impressive that Magnus Carlsen grew up in Norway, a country with very little chess tradition, is now the #1 player in the world, right? That appears to be a correct anecdote about the #1 player in the world. It just does not seem to be a generalizable anecdote. It appears that Magnus is as unusual potentially as other people who were in that position in a country with very little chess tradition. Similarly, age. Age did fall continuously, even when the Soviet Union was actively supporting chess, and in the decade after. But then it sort of flattened, right? So again, the age distribution among the top 300 players in the world falls from 1980 to 2000, doesn't do much when computers show up. And finally, the homogenization of chess style. Here, to go back to the question about the first 10 moves, we deliberately focused here on the first 10 moves. And we asked the question, over the first 10 moves of the game, is there a kind of increasing uniformity, increasing convergence on what to play in the open? Have chess engines contributed to that? That's only one of many ways we might have measured homogenization, but we're just sort of looking for possible measure. And again, a very faint dip as engines started to take over in 05 to 07, but relatively flat. So in other words, the folk wisdom about the impact on the professional chess ecosystem is not as clear-cut as it seems, right? And so there's this interesting divergence, because there is no doubt that chess has been monumentally transformed by the arrival of computers. It's been transformed for amateurs who can now play online and who can watch unlimited amounts of chess YouTube video. It's been transformed for the world's best players who can now train against chess engines. But it therefore becomes a particularly interesting question to look for where is the quantitative footprint of that? Like, where are the actual numbers that have actually moved? And that, I think, is an interesting question as we think about this as a case study of right? This rich creative human activity that's been upended by computers, and to actually look at what the effect is there as a sort of means of developing analogies with other domains. And so I'll stop there. This has all been about the ways in which, chess is, I think, really just a very interesting domain, for moving things out of the realm of speculation and into a setting where people with, unbelievably high levels of mastery are engaging in this cognitively complex activity, and to ask what we can actually learn by turning these algorithms on people, and thinking about issues of human behavior, thinking about what it means to simulate human behavior or to approximate human behavior, and to think about what the broader ecosystem looks like. So I'll stop there. Thanks very much, and happy to take more questions.
Yeah, I mean, I'm sorry to jump in, but yeah, I mean, I think that you are involved. You are involved in a really very effective experiment. I think with trying to look at judges on bail decisions.
Mm-hmm. Yes.
And I think similar questions arise there. Now they have programs that try to give them advice, and you have a program that's trying to imitate the behavior of judges. And what kind of conclusions can you draw to such domains?
So Sendhil and I have the work you're referring to is some work that Sendhil and Jens Ludwig at University of Chicago, a crime policy researcher, and I did with Yuri Leskovic and Hima Lakaraju, and the five of us looked at data on judges making decisions about bail. And Sendhil and I have thought a fair amount about, like, what are the connections here, right? These are obviously very different kinds of activities. In the case of bail, and again, a bit of background is perhaps in order. So pretrial detention hearings, which are obviously something, we came at that from a policy perspective, I think, because our pretrial detention system is sort of, in sort of urgent need of reform and some sort of rethinking of policy, and that's where Jens Ludwig sort of drew us into this work. But there's a particular sort of reason why algorithms are relevant there, which is the law says that a pretrial detention hearing where a judge decides where a defendant will wait for trial in the community or in jail calls on the judge to make a prediction, right? The judge should release the defendant before trial into the community if they believe that it is very likely that they will return for their court appearance without committing a crime in the meantime. And if they believe that there is too high a probability that they will either not return or commit a crime, then they're instructed to jail them, which is this incredibly destructive act. The person is going to wait in jail for 3 months. They may lose their job, they may lose custody of their children. There are all sorts of terrible things that happen. And so it's very important to sort of, as much as possible, find people who are low risk and to be able to release them. It's also, of course, there's a parallel movement to really sort of rethink all of the policy around this, which I think is a very important thing. Right, and so one huge difference, of course, well, there are so many surface level differences, including just the stakes of the decision. But at a sort of syntactic level, the bail decision is a prediction problem, right? I'm trying to do prediction from data. I say I have some features on this person, and I'm trying to make a prediction about their future behavior. And of course, I have a relatively thin set of features. There's bias in the training data just because, I mean, this is one of the most biased domains just because of the huge amounts of bias in discretion on arrest decisions and many other things. Whereas obviously in a domain like chess, it's a sort of cognitive puzzle solving activity. It's a complete information setting. And I'm trying to decide which of these options is going to sort of preserve the minimax value in some large but finite game tree. So I think that's an interesting, so I think there's sort of huge distinctions there. Having said that, I think, that too is a domain where there's a lot of interesting things to be learned about human error. And one thing that we did there was actually related to the decisions that we had to make about Maia 1100 on lead chess. We built a model that tried to simulate the judge's decisions, right? So in addition to trying to estimate ground truth, you say, let me simply build an algorithm that tries as much as possible to predict the decision the judge will make in this case. Let's forget what the defendant did in the future. Let's just decide what the judge is going to do. And then you can go back over the historical data and say, if I were to use the model of the judge, place the judge in every case that the judge heard, and make those decisions, where would you be with respect to the trade-off between release rate and amount of crime? And the answer is that the model of the judge creates a Pareto improvement over the human judge. They actually achieve lower crime with a greater release rate, right? Those things are supposed to move in opposition, but they don't. So what's going on? So there's, right, so it's, in shorthand, the model of you is doing better than you. And there's a number of theories as to why that may be happening, and there's been a bunch of empirical work since then. I think sort of the two big conjectures, the two big hypotheses there, which are related. One is that the judge is using signals that the algorithm doesn't have access to in the courtroom, right? So the algorithm sees the administrative data about the defendant. The judge sees the person in the courtroom. They talk to them, admittedly for only roughly 1 minute, often in many of these cases. And whatever it is they're using, these unobservables are probably hurting them, not helping, right? Because with access to these more features, they're doing worse. The other thing that's going on, of course, is that judges are likely making idiosyncratic decisions, right? So, you know, a judge is, you know, happens to make a mistake that they normally wouldn't have made, right? In other words, the model of you never accidentally leaves the keys at home, because on most days you don't leave the keys at home, but some days you do. And so in some sense, the other possible hypothesis is that the algorithm is sort of smoothing out the errors that the judge makes. And in that way, we were sort of reminded of all this when we released Maia 1100 on Lichess, because if Maia has a distribution over the moves that 1100 players make, it could either sample from that distribution or it could take the argmax. And when it takes the argmax, it of course plays much better, because a lot of the errors are happening from the heterogeneity, and arguably a lot of the judge errors are coming from heterogeneity. So I think that's definitely some linkage. But of course, the domains are extremely, extremely different, certainly. And yeah, you're putting oh yeah, so Maia is deterministic. So yeah, excellent question. Yeah, thanks, Shai. Yeah, so question from Danny, I think you can all see it in the chat. Yeah, so when we first put Maia out there, we had it start predicting from move 1, which meant you could replay games exactly. And so people would sort of, you know, kind of do a kind of Groundhog Day exercise where they would just keep playing the same thing, trying to find good things against it. I mean, admittedly, Maia is not that hard to beat, so, you know, but so we then actually added some things that kind of engage in quasi-randomization. So we have overt randomization at the beginning now. So now there's actually an opening book, which we derive simply from the opening book at rating X, right? So one nice thing about having all of the data is that you pick a rating X and you say, I don't need to go learn any openings. I'm just gonna, as long as there's enough coverage in the first few moves that players have been in this position many times, I'm gonna sample from the empirical distribution of what players in that, right? So I'm gonna start with memorization. I get to this point in the game, it's occurred 50 times, 30 times they played, you know, knight f3, and 20 times they played knight c3, and so I'm going to randomize 60%. I'm going to play knight f3, 30%. I'm going to 40%. I'm going to play knight c3, and so that creates overt randomization. And then once I'm into something which I've never seen before, I move out of memorization. I actually start running Maia. The other thing is that we are training a head that actually predicts the amount of time taken. And so by actually pulling from that distribution, we actually now can randomize the amount of time taken per move, which also induce a kind of quasi-randomization over the moves. That was another thing that we had to sort of, and so for all those reasons, it's no longer deterministic, and somehow the early issues with repetition don't seem to be a factor. Yeah, Nihar.
So I have a more basic question about the LO ratings itself. So as you may know, initially LO was assuming these normally distributed variables and the Thurstone model, and then they switched to logistics and the BTL model. Do you know if kind of the logistic and BTL still carries over for computer chess engines and also for the humans who are trained using computer chess engines? Or should we now think about changing it again?
Yeah, that's a good question. And so we've looked at this, and actually Lichess, there's interesting things to read on sort of Lichess and some of the ways they went to the Glyco2 rating, which is a sort of another variant on ELO. Yeah, this we have not. Yeah, this is something that we've begun to look at, but you would be in a better position than I would probably to sort of opine on this question, actually. it has been, obviously it's been a problem to sort of align ratings of humans and ratings of engines, because in some sense, there's obviously, in addition to all the other modeling aspects, there's obviously a translation and variance on ELO ratings, right? And so if I subtract 100 from everyone's ELO ratings, it makes the same predictions. And so the issue is, of course, once engines far surpass humans, it's almost like I now have these two disjoint components, connected components in the graph of who plays whom. And once I have, or at least I have extremely low conductance. And once I have extremely low conductance, these two things can begin to drift in ways that are hard to. So I think there's interesting questions that be to think about that sort of, it's a, like you could imagine having thought about like, what do I do with sort of player ratings in a world of very low conductance in the who plays who graph, but you might have asked, when does this arise? But this is exactly what's happening with engines and humans. So I think there's definitely some interesting questions there. And actually, if there's work there, there may in fact be work which I'm not aware of. Yeah, you were going to say something.
Yeah, I was just saying there was kind of a second question that's where maybe some engines like Maia might help, because they can provide the conductance from the super chess engines to humans maybe. Yeah,
and we're definitely trying this sort of, right, can Maia do some kind of interpolation and sort of a bunch of the questions there. And actually one thing, the highest Maia that we've released is 1900. We have kind of under development kind of, a 2100, a 2300. And part of the problem is that the human data falls off very fast at some point. It's still there at 2100, 2300, and we definitely want to release something at that level. But yeah, the kind of how do we sort of, can it be used in some way to help interpolate? I mean, I think it's also, we've discussed a lot a question that we don't yet have any real leverage on, which is sort of, could you create, it's sort of, there's two things that feel like they might be getting conflated, which is sort of playing at, say, a rating of 33,000 or 3,200 and making incomprehensible computer moves. And the interesting question is, one thing we're sort of trying with Maia-like ideas is, could you have something which plays at a rating of 3,000, but somehow fundamentally plays like a human being, right? Like, or is there some point at which to get to that rating, you're going to need to play these sort of incomprehensible tightrope-like variations that only computers can do? And it's a good question. Yeah, so I think all these are, interesting things in that. Ravi.
John, just a related quick question. I thought the way you were going to answer the style question was you would train Maia on the first decade, and then you would try to get it to predict the accuracy on the second decade and vice versa.
Yeah. That's we've talked about this. Part of it is it's a great question. We've talked about doing this, and because the only thing we've done with style has been very, very basic. That's sort of awaiting the following thing, which is currently Maia. We've been making progress on reducing the data requirements on Maia. I mean, so one issue is it's been helping that we have huge amounts of data in the present. As you go back from the past, you still have enough data, but you only have data for very good players, right? So like, if I look at games that were recorded in the 1980s, it's mainly among extremely good players. And Maia definitely has a harder time with very good players just because, the nature of how it's set up. I don't think it has to be that way, but at the moment that's been, it's been more successful on players that we're here. So I think, if we can get it to sort of simulate Grandmaster play better, then we can start looking at data from the 80s. And that's definitely something we hope to do. But it's a great point.
A quick question, does Maia do any search, or is it just purely the policy hit?
Yes, so this is actually a thing. I think I feel like there ought to be a way to make use of search. We have not been able to make use of search. So when we do search, the prediction quality goes down. And so it's basically, there is a value head that's estimating the probability the human will win the game, but that too is coming from the empirical data and not from any kind of tree search. And so, I think trying to actually make any non-trivial use of search in human move prediction in this framework, I think is a very interesting question, which feels like there ought to be some nice idea there, and we haven't found one.
The reason why I ask is because I think even strongest Leela network at without any search is only 1900 or 2000 or something like this. So you might be hitting that limit or something. I don't know. Yeah,
that's part of our problem. I think that I think we need to. Now, granted, strongest Leela without any search is not using games played by 2,300 players as training data, which we would be using that. But I agree that I think we are going to bump into something if we don't start. So in some sense, it makes it even more urgent to figure out how do we do a little bit of search if we want to actually get something. Gets up there. yeah, it's a great question.
All right. Any other questions, comments, or feedbacks for Jon? Okay. I guess then let's clap virtually for Jon. Let's basically thank Jon for attending the summer and give us this very interesting and fantastic talk. We hope to have you back at CMU, maybe physically in the post-pandemic world.
That'd be great. Yeah, no, I'd love to come back in person at some point and see everybody. And yeah, thanks for coming to the talk. It's yeah, and thanks for all the interesting questions.
Great. All right. Thank you, everyone. Thank you especially, Jon, for attending the seminar today. If you have any